Hello, and welcome to our understanding of water. Today we're going to do notes on Chapter 3. I would highly suggest that you print out the notes before you watch this video so that you can take notes literally writing on the paper, or at the very least you have a notebook in front of you so that you can jot down information as we go through the slides. So I hope you've taken a look at Chapter 3, Water and the Fitness of the Environment. That's what we're going to do now. So in front of you, you can see the Earth. Should be something you're aware of, something you've heard of before. On that picture, you can see all of the states of matter of water. We can see Antarctica at the bottom, which is ice, which is solid water. We can see the clouds, which is water vapor, and the blue oceans are liquid water. And it is because of the significant amount of liquid water that the Earth is as habitable and primed for life as it is. So water is extraordinarily important for our understanding of how living things can exist on Earth and why they do what they do. So let's dive in. A little pun. That molecule that supports all of life is water. Water is the biological medium on Earth. The medium is something in which other things happen. So chemical reactions are going to need water in order to interact with each other. If you take two powders and mix them, nothing happens. No reactions, etc. But as soon as you allow them to dissolve in water, you can get chemical reactions. All living organisms require water than any other substance. Most cells are surrounded by water, and cells themselves are about 70 to 95% water, depending on what type of cell you are. Obviously, we're not just talking about human cells here. For example, if we're talking about a pond water paramecium, they're going to be much more water than one of your skin cells. The abundance of water is the main reason Earth is habitable, and we're going to talk about why in a little bit. Now, water is a polar molecule. What does that mean? There is an unequal sharing of electrons. And that unequal sharing of electrons is going to make water polar because the opposite ends have opposite charges. The definition of polarity is opposite charges at opposite ends. Okay? Think about a magnet. When you were in third grade, you played with bar magnets. One end was the north, the other was the south. That had to do with the magnetic fields. Okay, and we know that magnetism and electricity are very closely related. Well, because of the electric particles, the electrons, we can create charges if we unequally share those electrons. So the polarity is caused by oxygen's high electronegativity. Water is made of one oxygen and two hydrogens. Oxygen and hydrogen have very different electronegativities. The oxygen has a much higher electronegativity than hydrogen. So the oxygen pulls on the electrons being shared in the covalent bonds closer to its nucleus. There are two covalent bonds in this molecule. These electrons are actually being shared closer to the nucleus of the oxygen than to the nucleus of the hydrogen. This makes oxygen slightly negative and hydrogen slightly positive. It is this charge separation that causes the polar molecule and gives the opposite ends opposite charges. Polarity allows water molecules to form hydrogen bonds with each other. So, what has happened? Okay, so polarity allows water molecules to form hydrogen bonds with each other. So, hydrogen bonding. The partial positive charge on the hydrogen is attracted to the partial negative of the oxygen. So because of the unequal sharing of electrons, we have partial positives and partial negatives. A partial charge is not a full charge. These are not ionic compounds. These are partial charges. Now you'll note the symbol that is being used is going to be this. It is actually the lowercase delta. It means partial. Uppercase delta, you'll remember, is going to be a triangle. Okay? This is lowercase delta and it means partial, so not fully. These partial charges are going to act like small magnets and they're going to attract each other and they're going to create weak bonds. These weak bonds are hydrogen bonds. They're called hydrogen bonds because most of the time they happen where a hydrogen is involved. Each individual water molecule can create 4 hydrogen bonds with other water molecules nearby. Now, because of the hydrogen bonds, water has some special properties. 4 of water's properties that facilitate an environment on life are as follows: cohesive behavior, ability to moderate temperature, versatility as a solvent, and expansion upon freezing. You need to know those 4. Now, I've put them in this particular order because they happen to spell out a mnemonic device, CAVE. If you can remember CAVE, you can easily remember the 4 properties of water. C for cohesive behavior, A for ability to moderate temperature, V for versatility as a solvent, and E is for expansion upon freezing. These unique properties result from the structure of the interaction of the water particles themselves, specifically the hydrogen bonds. So let's talk about cohesion and adhesion. At any instant, a substantial percentage of all water molecules are bonded to their neighbors, creating a high level of structure. We all know this because we all understand what surface tension is. More on that later. Collectively, hydrogen bonds hold water together, a phenomenon called cohesion. Cohesion is going to be alike things stick to each other. Okay? If you have a cohesive team, everyone's working together. So cohesion means stick to each other. Hydrogen bonds also make water molecules stick to things, stuff, other substances. That's adhesion. Okay? Like adhesive tape sticks to other things. Tape would be pretty crappy if it just stuck to itself. So we want it to stick to other things. It is through these two properties that plants have such an effective water transport system. Capillary action. Now, capillary action is actually the movement of any fluid through a tube. The particular fluid movement of fluid through a tree and a plant is actually known as transpiration. Now, transpiration is driven, the water is driven up the tree by evaporation. Water evaporates from the leaves, and that evaporation causes a vacuum to form, and that vacuum, like a straw, literally sucks water up the tube like a giant conga line, and we get this movement. Now, what causes the movement and evaporation of the water from the top of the tree? The sun. The sun heats up, providing energy to the leaves and causing evaporation. We also have photosynthesis going on, which is going to remove some water, so we need to keep replacing that water that's used and supplying it from the roots. So the roots pull it up from the ground where it got into the ground by precipitation, and then it moves up the tree and out the leaves through transpiration, both of which enabled by the cohesion between the water molecules and the adhesion against the sides of the xylem, which enable the water to repulse the pull of gravity. So we start at the bottom. Water got here through precipitation. It travels up the tree through cohesion and adhesion and capillary action, and out the leaves through evaporation. So evapotranspiration is driven by the sun. Surface tension is dependent upon capillary cohesion. Surface tension is a measure of how hard it is to break the surface of a liquid. If you've ever done a belly flop into the pool, and you've contacted the water and it's hurt, and you've cried, and you've turned bright red, you have understood surface tension. So you've played Red Rover with the water, and you failed. So surface tension is related to cohesion. Surface tension keeps both the coin and the water strider from falling through the water. Moderation of temperature. Water stabilizes air temperature by absorbing heat from warmer air and releasing heat to cooler air. So the reason water can maintain its temperature is because it has a high specific heat. It takes a significant amount of energy to move the temperature of water. Because what you're actually doing is breaking the hydrogen bonds first before you can increase the kinetic energy of the water molecule. Remember, temperature is a measure, it's a molecular speedometer. It's a measure of the movement of molecules. More kinetic energy, more temperature. So by adding heat to water, you want to increase the movement of the water molecules, but you can't until you break the hydrogen bonds. Because of the significant density and the amount of the hydrogen bonds, you need more energy. Now, specific heat has a particular measurement. Specific heat of a substance is the amount of heat that must be absorbed or lost for 1 gram of that substance to change its temperature by 1 degree Celsius. Different substances have different specific heats. It is much easier to change the temperature of metal than it is to change the temperature of water. So, for example, I can take a pot of water and put it on the stove. I want to make mac and cheese. I put the water on the stove. I turn the stove on. Fire comes on. It's burning underneath the pot. It's on for about 1.5 minutes, 2 minutes. I decide I don't want mac and cheese anymore. Not because I don't like mac and cheese. Mac and cheese is awesome. But I just got a text. Mom's bringing home dinner. Don't eat anything. I would probably still have the mac and cheese. But regardless, I turn off the oven. Would I put my finger under the bottom of the pan? Absolutely not. 90 seconds is enough to make that metal hot enough that it could burn me. Could I put my finger in the water? Totally possible. Depending on the starting temperature of the water, it might just be lukewarm at this point because 90 seconds might not be enough time to get enough energy into the water to move it to a significant amount. Why? Because water has a much higher specific heat than metal. Water's high specific heat is due to the hydrogen bonds. When energy is added, it's used to break the bonds, the hydrogen bonds, not increase the kinetic energy of the molecules. It is this consistency that enables water to moderate temperatures on Earth because they don't dramatically increase or decrease in temperature rapidly. They're able to absorb a significant amount of energy or release a significant amount of energy. Vast quantities of plant and animal life are able to survive at these temperatures. And organisms rely on water to help maintain their own temperature. So doing homeostasis. For example, sweating. Evaporation is a cooling process. As water leaves your body through evaporation, it takes energy with it and therefore cools you down. Water is also the solvent of life. So we talked about the fact that we've got cohesion and adhesion. We talked about the ability to moderate temperature. And now we talk about versatility as a solvent. A solution is a liquid that's a homogeneous mixture of substances. A solvent is the dissolving agent of a solution. A solute is the substance that is dissolved. Water is a versatile solvent. In fact, it's known as the universal solvent because of its polarity. An aqueous solution is one in which water is the solvent. So an example of an aqueous solution might be salt water. Salt water. There's two compounds here, salt and water. Salt is the solute. It is the substance that's being dissolved. Water is the solvent. It's the dissolving agent. It's what's doing the dissolving. So let's take a look at how it does this. Water is an effective solvent because it readily forms hydrogen bonds. Everything comes back to hydrogen bonds. Why does water do cohesion? Hydrogen bonds. Why does it do adhesion? Hydrogen bonds. Why is it good at moderating temperature? Hydrogen bonds need to be broken before the energy is able to increase the kinetic energy of the water molecules. Why is it a good solvent? Hydrogen bonds! Water can form hydrogen bonds with other molecules. For example, anything that's polar will be able to dissolve in water. Anything that's ionic or charged will be able to dissolve in water. When an ionic compound is dissolved in water, each ion is surrounded by a sphere of water molecules known as a hydration shell. So in this visual, we've got NaCl. NaCl is represented by the green and yellow dots. Okay? The green and yellow dots are going to be either sodium or chlorine. Now, based upon this visual, you should be able to determine which one is sodium and which one is chlorine. So take a moment, pause me if you need to, but determine which one is sodium, Na, and which one is chlorine, Cl. So jot this down on your paper. Sodium equals Cl, chlorine equals, and write the color next to it. Your choices are green and yellow. All right, welcome back. I assumed you paused me, and now you've returned with your answers. If you said green was chlorine and yellow was sodium, you are correct. How do we know this? We look at the orientation of the water molecules. Sodium is going to be positive. It's going to lose an electron to chlorine during the ionic bond formation. And therefore, it's going to attract the negative oxygens. If you can see the orientation of the water molecules, all of the negative oxygens are facing the yellow dot. Therefore, that has to be positive. As for chlorine, chlorine gains an electron, meaning it's going to be negative, and all of the positive hydrogens are going to face chlorine. Now, I would have gone by the orientation of the water molecules. If you said green was chlorine because chlorine's atomic number is 17, and sodium is yellow because yellow is smaller, and sodium's atomic number is 11, and therefore it would have a smaller atomic radius, I don't disagree, but you're also putting a significant amount of faith in the artist who drew this picture for this textbook that they were going to be on the money with the atomic radii. So use the orientation of the water molecules. Dissolving polar and nonpolar. So water can also dissolve compounds made of non-ionic polar molecules. Okay? Even large polar molecules such as proteins can dissolve in water if they have ionic and polar regions. So this is a lysozyme. It's clearly an enzyme, which means it's going to be a protein. And it is in an aqueous environment. And as we can see, the water molecules surround it, creating a giant hydration shell because they're able to form bonds, hydrogen bonds, with the different R groups that make up the protein. All right, so substances interacting with water can be named hydrophilic or hydrophobic. A hydrophilic substance is one that has an affinity for water. A hydrophobic substance is one that does not have an affinity for water. Hydro, water, philic, from the Greek word meaning love. So water loving is a hydrophilic substance. Hydro, water, phobic, fear. Okay, so phobia is the same word that comes from that root word. Hydrophobic means water fearing. So molecules that are going to be polar are going to be hydrophilic, like sodium and chlorine. And fat, which is a nonpolar hydrocarbon, is going to be hydrophobic and therefore will not dissolve in water. This is why oil and water don't mix. Hydrogen bonds sink the Titanic. True story. Ice floats. And this is our final water property of water. Expansion upon freezing. Ice floats in liquid water because hydrogen bonds in ice are more ordered, making the ice less dense. If ice sank, all bodies of water would eventually freeze solid, making life impossible on Earth. That's bad. So let's take a look at why this happens. So here's gaseous water, water vapor. The water molecules are fairly spread out. Here's liquid water. They're all jammed together, but they're moving around, breaking and making hydrogen bonds. And then we've got solid water. What's interesting is we see a regular geometric pattern. And in fact, because of this regular geometric pattern, the water molecules are actually more spread out in the solid than they are in the liquid. This is very unusual. Most times when you go from gas to liquid to solid, you're going to be packing closer and closer together, and you're actually going to increase your density, but that's not so with water. Water does whatever it wants. It's fairly magical. So let's take a look at this repeating geometric pattern. This is known as a lattice structure. As we remove energy from the system, we decrease the kinetic energy of the water molecules. As we decrease the kinetic energy of the water molecules, they're not able to slip by each other as easily. They slow down and they actually get held in place by the hydrogen bonds. Because they get held in place, they start to form this repeating geometric pattern that has empty space. Now, if there's a question on the test and it says, why does ice float? The answer is not because there's air in there. There is no air in this empty space. All there is empty space. What we've done is we have not increased the mass of the amount of water that we have. We didn't pick up water, we didn't lose water. We didn't change our mass. What we did was we changed our volume. If you recall back to freshman year, you should have learned that density equals, and I would write this down, D equals, get ready for it, mass over volume. Okay? Density equals mass over volume. So M over V. What is the relationship between density and volume? Well, because volume is in the denominator, the relationship is inverse. So as one goes up, the other goes down. Mass does not change. We didn't get any more water molecules. We just changed the volume. As we increase volume, then, we're going to decrease density. So the ice is actually going to be less dense than the liquid water that is surrounding it, and so therefore it will float. This is something you're going to need to be able to explain. You can't just say ice floats because it's less dense than water. You need to explain to me why it's less dense than water. And the answer is because ice takes up more volume than the same amount of liquid water, right? The same mass of liquid water, and therefore, because volume and density are inversely proportional, the density goes down, and therefore the ice can float. Now, dissociation of water. Water dissociates. It actually breaks. And because of that, it's going to lead to acidic and basic conditions. A hydrogen atom and a hydrogen bond between two water molecules can shift from one to the other and is transferred as a proton or hydrogen ion. So for us in biology, a hydrogen ion, H+, and a proton, those are going to be synonyms. We're going to be able to use those interchangeably. So when I say proton, I mean H+, and when I say H+, I mean proton. The molecule with the extra proton is now a hydronium ion. So a water molecule is literally going to pick up an H+ ion and become H3O+. The molecule that lost the proton is now a hydroxide ion, OH minus. So this is the dissociation of water. You need to have two water molecules because you can't just jettison a hydrogen. You can't just let that body run. It's like a small child. Okay? Somebody's got to pick this bad boy up. Okay? You can't just let children run around willy-nilly. Somebody's got to keep an eye on them. Apparently it's frowned upon to let them run wild. So what happens? We lose a hydrogen. Okay? These water molecules are interacting with each other through a hydrogen bond. One hydrogen is going to leave and be picked up by the other. As it does so, you'll notice that both of these water molecules do not have a charge, right? We said that they were polar, which meant that they had opposite charges at opposite ends, but they were partial charges. The net charge was 0. So when we pick up this hydrogen, we're picking up another proton. That proton is a positively charged subatomic particle. So what are we going to pick up? We're going to pick up a positive charge. A full positive charge. Not a partial, but a full. And we've got our hydroxide ion. And that hydroxide ion lost a proton. So therefore, the electrons and the protons are no longer balanced, and the hydroxide ion is going to pick up a negative charge. Dissociation creates ions. By definition, dissociation is breaking into ions of opposite charges. So we can dissociate Na and Cl. In fact, Na and Cl do dissociate in water. They dissociate into Na plus and Cl minus. We can dissociate hydrochloric acid down here at the bottom. Hydrochloric acid dissociates into H plus and Cl minus. Sodium hydroxide is going to dissociate into Na plus and OH minus because of the interaction with water molecules. We'll get into weak acids and weak bases down the road. These have to do with functional groups, and we'll talk about functional groups. C double bond OOH, this is actually going to be a carboxyl group. That is a weak acid. And NH2 is an amine group, and that's a weak base. More on that in Chapter 4. Okay? For right now, keep in mind that you can have strong acids and strong bases, and weak acids and weak bases. So hydrochloric acid is a strong acid. Sodium hydroxide is a strong base because they completely dissociate. Carboxyl groups are a weak acid, and amine groups are a weak base. Again, we'll discuss more about that down the road and how they are a strong acid and a strong base and a weak acid and a weak base, but just so you know, it's because of dissociation. All right. We're talking about acids and bases. We must talk about the pH scale. Concentrations of H plus and OH minus are always equal and balanced, okay, in pure water. Adding certain solutes called acids and bases modifies the concentrations of H plus and OH minus and changes them. Biologists use something called the pH scale to describe how acidic or basic a condition is. An acid is a substance. And now, you can have many definitions of acids. This is the definition we choose for biology. There's different definitions for chemistry, okay? But we're going to go with an acid is a substance that increases the H plus concentration of a solution. So it is a proton donor. A base is any substance that reduces the H plus concentration of a solution. It is a proton acceptor. So the pH scale, and people are always like, where's pH coming from? It's actually, we have hydrogen, French, means hydrogen power. You want to know how much hydrogen there is. So we're looking at the H plus. I apologize to anyone who is actually French or speaks French or has ears. That was a pretty bad French accent. The negative logarithm of the concentration of hydrogen ions in moles per liter. So excellent, it's a logarithmic scale, which means it's going to go up hella fast, right? It's going to be based on jumps of 10. So we're going to go up in magnitude fairly quickly. The difference between a pH of 4 and a pH of 5 is 10 times. The difference between pH 4 and a pH 6 is 100 times. So pure water equals 1 over 10 million moles of hydrogen ions. That's 0.0000001 mole per liter. That's 10 to the negative 7 moles per liter, or a pH of 7. That's neutral. So there's the same amount of hydrogen ions as there is hydroxide ions. A pH of a solution is determined by the relative concentration of hydrogen ions. Acidic solutions have a pH value less than 7. So the pH scale goes from 0 to 7. The pH scale goes from 0 to 14. Acids go from 0 to 7. Basic solutions have a pH value greater than 7, so 7 to 14. Most biological fluids have a pH value in the range from 6 to 8, so we don't want to get too crazy. Because it doesn't matter. People are always like, oh, acids are so much worse than bases. Bases are just as bad. The further you get away from neutral, the worse they are, the more corrosive they are. The way I like to look at the pH scale is, do I want to put my finger in it? The further away I get from 7, the less likely I want to put my finger in it. Right? Here's 7, pure water. I'll put my finger in pure water. Human blood, that has happened, right? Seawater, I've been swimming. Urine, we've all been there, right? Black coffee, maybe. Tomato juice, it might sting a little bit. Lemon juice, not if I've got a cut. That's going to hurt, right? Gastric juice, my finger's going to get eaten and digested. This is not good, right? You want to put your finger in oven cleaner? I don't think so. So stay away. Okay. Buffers! The internal pH of most living cells must remain close to 7. So we need a way of making sure that happens. We need to maintain homeostasis. Random things are going to get in and mess stuff up. So we need to have buffers. Buffers are substances that minimize changes in concentrations of H plus and OH minus in a solution. Most buffers consist of an acid-base pair that reversibly combine with an H plus. Interestingly enough, a buffer is not a compound in and of itself, but rather a chemical reaction. So combinations of H plus donors and H plus acceptors forms a weak acid-base pair. Okay, so let's say that you breathe, which you normally do since you're alive, and you have an additional amount of carbon dioxide. Okay, so you've been undergoing respiration and you've made CO2. CO2 gets in your blood and mixes with water that's in there. Your blood is significantly made of water. H2O plus CO2 actually makes a compound called carbonic acid, which is going to be H2CO3. H2CO3 in the water is going to be a weak acid and can actually dissociate into H plus and HCO3 minus. So if we let this reaction go, we're going to get HCO3 minus on this side plus H3O plus. So when H plus came off the H2CO3 and it became H2CO3 minus, and that H plus went and got accepted by the water, and that became H3O plus. Remember, a weak acid is a proton donor. So in this particular case, carbonic acid is the weak acid. Water, interestingly enough, can be both an acid and a base. So we saw in dissociation, water becoming H3O plus and OH minus. In that particular case, water was acting as an acid. In this particular case, H2O is picking up that H plus ion and becoming H3O plus. So it's acting as a weak base. So you've got a weak acid and a weak base on the left. And you've got carbonic acid, which is now a weak base, and H3O plus, which is hydronium ion, which is a weak acid. So you actually have a weak acid and a weak base and a conjugate base, because the weak acid turns into HCO3 minus. It's actually known as a conjugate base because it's the pair, okay? And then the H2O becomes H3O plus. So this is the weak base, okay? H2O is the weak base, and H3O plus is the conjugate acid because the weak base turned into the conjugate acid when it picked up the H plus ion. So carbonic acid and bicarbonate, this is your weak acid, weak base pair that make up the carbonic acid bicarbonate buffer. So when I said the buffers are typically a weak acid base pair that reversibly combines, this right here, forget about this guy. Don't look at this. This H2CO3 plus H2O yields HCO3 minus plus H3O plus. That is the carbonic acid bicarbonate buffer. And in fact, this should be a reversible arrow, because this reaction can go both ways, depending upon what you need to do to maintain your pH. Remember, it doesn't make it neutral, it just maintains a stable pH. So if my blood needs to maintain a stable pH, my blood's pH is not 7. In fact, it's 7.4. It's slightly basic. If my pH of my blood was 7, I'd have a little bit of difficulty. I wouldn't be happy. My things and enzymes wouldn't be working as well. So I need to use the carbonic acid bicarbonate buffer to maintain a stable pH of 7.4 in my blood. Please make sure you take a look at the study guide. There's an interactive question that deals with this, and it's a very good question that enables you to understand what's going on. Take a look at that, and if you have any questions, we'll talk about it tomorrow. The threat of acid precipitation. Acid precipitation refers to rain, snow, or fog with a pH lower than 5.6. Acid precipitation is caused mainly by the mixing of different pollutants with water in the air, like sulfur, dioxides. Acid precipitation can damage life in lakes and streams. So rain or fog with a pH lower than 5.6 acidifies lakes and streams, leaches good minerals like calcium and magnesium out of the soil, and concentrate toxins like aluminum. Aluminum may be great when it's in a can holding soda, but it's bad when it gets in your blood. Sulfur oxides and nitrogen oxides from burning of fossil fuels are going to directly increase the amount of acid rain. The effects of acid precipitation on soil chemistry are contributing to the decline of North American and European forests. That's bad. In addition, we're getting acidification of Earth's oceans. Now, Absorption of CO2 into the ocean leads to acidification. So CO2 is produced by breathing. Sure, that's not the problem. The problem is burning fossil fuels. As a jetliner flies across the sky, it's burning a significant amount of fossil fuels, releasing a significant amount of CO2. The CO2 enters the oceans. The CO2 combines with H2O, creating H2CO3. Oh, we've already seen that. That just happened. We were in the blood and we saw carbonic acid. Now we're in the ocean and we see carbonic acid. Well, that's unfortunate because seawater is supposed to be basic. And now we're seeing the increase in acid. So what happens? Well, that carbonic acid is going to deprotonate, as acids are wont to do. It's going to lose an H plus ion. And it's going to then interact with carbonate that is in the ocean. Now, how did carbonate get in the ocean? Well, calcium carbonate is in the ocean. Calcium carbonate makes up marine shells and coral. Well, guess what? If the calcium carbonate is breaking up, if it's dissociating, it's because it's interacting with acids. So the acidification of the ocean is actually going to decrease carbonate, and it's going to eat away at marine shells and coral. And how will that affect coral reef ecology? It will destroy it. Is this good or bad? This is very bad. This is no good. So we need to work on this. Okay, we need to fix this. Make sure you're ready for that. Okay? All right. Let's make sure we're on the same page. Hydrogen bonds. Each water molecule can create 4 hydrogen bonds, right? Because of the partial charges. Okay? Please remember that the partial negative of the oxygen is actually equal to both the partial positives on the hydrogens. So that's important to know because remember that water is, in fact, a completely neutral molecule. One water molecule can form 4 hydrogen bonds, but within like a cup of water, there could be billions of hydrogen bonds. So we understand that there are 2 polar covalent bonds within one water molecule, but each water molecule can form 4 hydrogen bonds around it. We know that water is the universal solvent because it can surround ions from ionic compounds and thus create hydration shells. That's going to dissolve things. It can do this because it has hydrogen bonds. Water is everywhere and beautiful. This is your moment of Zen. Please make sure that you've got questions. We're going to go through this. We've done the lecture. We are now going to make sure that you completely understand it. Make sure that you take a look at the reading guide. You don't have to finish it, but you should definitely understand water by tomorrow. Thank you.